Please listen carefully.
Hello and welcome to GasGasGas, the podcast that covers the FRCA primary exam. We're going to fit into your day and give you as much of your life back as you could possibly imagine. I'm here to make your studying easier. Listen to us on your commute, in the gym, in the shower, or when you're ironing your scrubs. Expect facts, concepts, model answers and the odd tangent. Check out the show notes for all the detail and remember to follow the show so that you never miss an episode. Let's get on with it. Hello everyone, this is James at GasGasGas. This is more VivaCast action with our willing victim Tom. He finds himself away in to quite a heavy session. I've decided to split this physiology section down into 3 subsets because otherwise it's just too much to learn, I think, in one go. And you just melt your brain. We're going to do blood pressure, coronary perfusion pressure, flow resistance, and dip our toe into the cardiac cycle. All core stuff that you should be able to wang the keywords out for. Let's get on with it.
Okay, Tom, we're beavering away and we're making excellent forward progress, and we are now an hour and a half into our Viva action. The smile on your face has actually gotten bigger, not smaller. Are you ready for your physiology Viva? My favourite topic, physiology. I've got a favourite textbook. We'll talk about that after. What is blood pressure and what governs it?
So, blood pressure.
Sorry everyone, this is just a brief technical delay whilst we iron out a few kinks with our technology. As you well know, we're a heavily funded podcast company with a budget that runs into the millions, so this sort of thing happens very rarely. Unfortunately, here we are now. I hope Tom is back in the room. Tom, can you hear us?
Yeah.
Spiffing.
So, blood pressure is a measure of pressure within your arterial system. So pressure itself is equal to force over area, and if you measure the force over the area within your arteries, it gives you an arterial blood pressure. You can also measure blood pressure in various other parts of the vascular, such as central venous pressure, right atrial pressures and things like that. Can you repeat the question? Sorry, I think there was another section to it other than what is blood pressure.
What is blood pressure, but what governs it?
So blood pressure is governed importantly by your cardiac output and by your systemic vascular resistance. So cardiac output is equal to stroke volume times your heart rate. So increases in heart rate and increases in stroke volume will lead to increases in blood pressure as higher amounts of blood per unit time are ejected from the heart. And the vasoconstriction of your small vessels will be extremely important in dictating pressure within your vascular system as well, due to the Hagen-Poiseuille equation. So laminar flow, which is normal flow within arterial vessels, is equal to pi times the radius of the vessel to the power of 4 times the pressure difference across the system divided by 8 times the length of the vessel and multiplied by the viscosity, which is nu.
And could you just talk me through, when you're mentioning resistance there, increases in resistance are proportional to what, or inversely proportional to such?
So as the radius of blood vessels and particularly arterioles decreases, resistance and pressure increase together. And as the radius of them increases, then conversely your blood pressure decreases, as does resistance. So as we mentioned the Hagen-Poiseuille equation before, Q equals pi r to the 4 delta P over 8 L nu. You'll notice that the radius of the vessels is going to have a really significant effect because it's to the 4th power, and so changes in vessel size will have a large effect on blood pressure. So as they decrease, flow will decrease and pressure will increase, and the converse is also true. Other things that affect blood pressure include the...
How does viscosity affect the resistance in the system?
So as viscosity increases, resistance also increases in direct proportion. So viscous blood, so blood with a high hematocrit or with a low temperature will lead to increased resistance in the vasculature.
And length?
So yeah, length. So as I mentioned before, so flow is inversely proportional to 8L nu. So as length increases, resistance also increases. And if you think of multiple vessels, can be thought of really as one longer vessel. Increased number of vessels, so increased numbers of tissues to supply, will also increase resistance, such as in obese patients.
So you mentioned that this is reliant on flow in a laminar system. What's the contrary to laminar flow?
So turbulent flow is another type of flow that occurs within certain systems, and different things affect the rate of flow within a turbulent system versus a system at laminar flow. So when turbulence is an important factor, the radius of the vessels or tubing that a fluid flows through is still important, but only R to the 2 rather than R to the 4, so it has a smaller impact. Length remains important in systems with turbulent flow, but viscosity becomes less important, and the density of the fluid that's flowing turbulently is more important. So as density decreases, flow increases within a turbulent system. An important application of this can be the use of heliox in asthmatic patients. So as their bronchioles constrict, they develop turbulent flow within their airways, and that flow can be increased proportionally to the decreased density of the air they're breathing. So adding helium decreases the density of the inspired gases and means they can increase flow within their small airways.
Excellent stuff. So moving on to thinking about flow in some particular vessels, how does flow differ between the left and right coronary arteries throughout the cardiac cycle?
The left coronary artery is more significantly impacted by ventricular systole, as the relatively large and muscular left ventricle contracts. It constricts the radius of that vessel, decreasing flow and increasing pressure within the left coronary artery. You still have some increase in pressure and decrease in flow in the right coronary artery during ventricular systole, but to a much lesser extent due to the lower pressures in the right side of the heart and the reduced muscle wall thickness.
So it sounds like flow is dependent on whereabouts in the cardiac cycle you are.
Most flow happens via the left coronary artery during diastole, and in the right coronary artery you get proportionally, there is still more blood supply during diastole, but there is a larger proportion of blood delivered during systole.
So you mentioned diastole and systole there. Could you break down the cardiac cycle for me into its components?
So we can begin thinking about the cardiac cycle as ventricular diastole initially. So this is the end of ventricular systole. As the right and left ventricles relax, then pressure drops in the ventricles. As the pressure in the atria becomes greater than that in the ventricles, the mitral and tricuspid valves open and we get filling of the left and right ventricles. Towards the end of their filling, we have atrial systole, where the atria contract and complete the filling of the ventricles, and this is closely followed by ventricular contraction. This can be divided into several different parts of the cycle. So initially we have, so I can't remember the terminology actually, but initially we have contraction, but prior to the pulmonary and aortic valves opening, we have contraction with a constant volume. Isovolumetric contraction, that's what it's called.
It is indeed, yeah.
And the muscle of the ventricular walls contracts. You get a sharp increase in pressure in the ventricles, and then at some point the pressure in the ventricles exceeds the pulmonary or aortic valves respectively, and you move into the next phase, which is rapid ejection. So here we have a large pressure difference between the left ventricle and the aorta, and between the right ventricle and the pulmonary arteries, and so we have rapid ejection of blood through that part of systole. We then move into isovolumetric relaxation, which is like the converse part of the cycle.
Lovely. There we have it. So just so we're all exactly the same page, I'm going to blast through the key points. Pressure is force over area, or stress, also force over area. We know that pressure is guided by flow and resistance. This is Darcy's law. We know that the formula for pressure in our human, calculating the mean arterial pressure in our system, is cardiac output times systemic vascular resistance. We can work out systemic vascular resistance by subtracting the central venous pressure from the mean arterial pressure and dividing it by the cardiac output. That's how they interrelate anyway. When we're thinking about flow in a system or resistance in a system, which is what I'm more interested in really, the resistance for flow in a tube that follows most of the rules, i.e. it's laminar, resistance equals 8 times the viscosity of the liquid times the length divided by pi times radius to the power of 4. So we all know that that means that resistance is inversely proportional to the radius to the power of 4. So that's the most important thing. You can also manipulate viscosity by putting more crystalloid in someone. You can't really alter length, really, but I suppose you could cut their limbs off. Although very extreme, you would reduce peripheral vascular resistance that way. Dark. And actually, interestingly, once upon a time for heart failure, they used to put sequential tourniquets on people's arms and legs, allowing the legs to fill from a venous perspective, because they'd occlude the venous pressure but allow the arterial pressure to prevail. So you could fill a leg with all the fluid in a person and therefore offload their heart transiently. You can imagine that this doesn't really work for a very long time, but it's a cool thing to think about. Then we touched upon laminar versus turbulent flow, and the thing that helps you guide between is it going to be turbulent, is it not going to be turbulent, is Reynolds number. Reynolds number is a dimensionless number. If the number is greater than about 2000, odds are it's going to be turbulent. The formula for Reynolds number is the velocity of the fluid times the density of the material, fluid, gas, whatever, times the diameter of the thing you're running down divided by the viscosity. So there you can infer that it's inversely proportional to the viscosity and proportional to the velocity, the density, and the diameter. We then talked about flow in coronary arteries. The big hitters here is that the left ventricle is perfused only in diastole, whereas the right ventricle is perfused throughout systole and diastole. This means that the right ventricle is probably less conditioned than the left ventricle when it comes to being exposed to ischemia, because that right ventricle is having a delightful time getting oxygen throughout the whole cycle with a few shifts in flow, whereas the left ventricle only gets that delight in diastole, so it's a bit more conditioned to tolerating a period of low perfusion. Protect the right ventricle. And then we touched on cardiac cycle. This is something you just need to be able to barf out, ideally with perhaps a few little bits of extra flair alongside. I'm just going to tell you that it's atrial systole, isovolumetric contraction, and then it's rapid and then reduced ejection, isovolumetric relaxation, and then rapid and reduced filling. Have a look at the show notes. Thank you very much for listening, guys. Ta-ra!
Thanks for listening to that episode, guys. If you found it useful or awful, please like and subscribe and rate the show. Definitely go check out those show notes on GasGasGas.uk. We all know that this is a bucket of content. I want you to take some time for yourself and don't overcook it. Don't freak out. Keep studying.